Hey everyone, so now you know how to do electron configuration. We're going to go through and talk about some perspective for electron configuration. So now that we can write out these really complex configurations, what does that mean? So let's get started by kind of picking up where we left off, and let's look at a periodic table and let's label part of it. So for our periodic table, we know that we want to move helium. Let's move helium over here. And now it's part of the S block. So let's label our blocks. We've got S, P, D, and now we have F. We know when we get to the D block, we subtract 1, and the F block, we subtract 2, and that is from the number out front. And we've got 7 rows there on the periodic table we're looking at. So now let's start to figure out what this means. So whenever you write your electron configuration, we notice that we are always starting with hydrogen. And that means we always start with 1s. Every single element on the periodic table will have a 1s orbital. And then after that, we go across the rows or across periods, to use our vocabulary word. Now for that perspective. So all of these numbers that you would write, like 1s2, 2s2 from this row number. So these row numbers, what you're actually doing is you are writing down energy levels. So energy levels are the row number. The only exception would be the D and F block. So except D and F block. So just like how on Bohr's model we had energy levels, like the first energy level, well, here's our first energy level. And you notice only 2 elements can fit in that first energy level, 2 electrons. Well, that first energy level for Bohr had a maximum of 2 as well. Then we went to the second energy level, just like Bohr had a second energy. On the electron configuration, our second energy level is split. Part of it's in the S and part of it's in P. But in total, if we counted across, we'd see 1, 2, 3, 4, 5, 6, 7, 8. And coincidentally enough, 8 electrons could fit in the second energy level of Bohr's as well. Interesting. The difference here with electron configuration is that instead of all of them being in the same energy level, we're showing, well, they're in the same energy level, but we're showing where they are in terms of a shape and a sub-level. So we have these different shapes that are blocks. So when you hear S, P, D, or F, you need to start thinking about shapes. For example, when you see S, you're going to start to think sphere. The S shape is a sphere, just like you see there. And that's the shape of the orbital. It's a 3-dimensional space where the electron could possibly be found. If you hear a p orbital or CP, you are going to start to think of the shape dumbbell. And that makes sense. That kind of looks like a dumbbell. We could be lifting that. And then if you see the sublevel D, you're going to start to think of cloverleaf as a shape. Now, I know that only 4 of them really look like that cloverleaf shape. This one on the left does not. There are exceptions to every rule. And you're also going to notice we did not write down the F block. And that's because the shape for the F block is just complex. They're funky and we're not going to worry about them. But you do need to know that S is sphere, P is dumbbell, and D is cloverleaf. So here's what that means. Let's say we are looking at a model of an atom, and we're going to go through its electron configuration. So we start out, and we always know that nucleus is here in the center. So there's our nucleus in the center, and we're going to get rid of that, but we know that it's there. When we do the electron configuration, the first thing that comes up is 1s. So this 1 is telling us the energy level. So it's a pretty low energy, and then S is referring to the shape. So we can see the shape on there is a sphere. After 1s comes 2s. So 2s, 2, we have a slightly larger energy level, and S, we have a sphere shape. So the second S, 2s, would have more energy than the first S. After 2s, if you go across the periodic table, then you're going to see 2p. So now we've got 2p. So this is 2px. You'll notice in the picture on our notes that there were 3 different ways the p orbital could be. three different orientations, three different orbitals. The first goes on the x-axis. So there's x, y, and 2pz showing up on the y-axis and the z-axis. So that would be the second energy level. But now we're at a p orbital, which does have a slightly higher energy than that s. After 2p comes 3s. After 3s is 3p. So 3s, we can see that blue sphere, third energy level, slightly larger. And then we've got 3px, and now we can see our third energy level on that p shape. And we've got y and z, and then we could keep going to 4s like that. So really, this is what an atom looks like. These different regions of space where the electrons can exist in these orbitals. We know that atoms aren't just circles now with electrons orbiting it. That is outdate. We know that that's not the case. Electrons exist in these different shapes and orbitals. And that's what the electron configuration is telling you. It is telling you exactly where every single electron is and what shape it's at, and what energy level it's at. So let's label our electron configuration parts. So this number out front, this is the energy level. Tells you how close it is to the nucleus, how much energy is in there. And the next thing we see, whether it's S or P, D or F, these are the shapes of the orbitals. Then the last thing we see, this tiny number at the top, these are the number of electrons in each of those orbitals. So in this 1s2, which we said would be a really small sphere there are 2 electrons. And then we go to a 2s around that, we can imagine, and then there would be 2 more electrons, and so on and so forth. So that's telling us how many electrons there are. And of course, that rule for the electron configuration is always go in the correct order. We always want to be going across in the correct order. Let's jot down an example of electron configuration. Why don't you write down the electron configuration for argon? Pause the video, test your memory, and see if you can write down the configuration for argon. Okay, your configuration should look like this: 1s2, 2s2, 2p6, 3s2, 3p6. If you struggled with that, then you need to go back and watch the previous video. All right, let's do some more practice. So let's do some examples. So you have quite a few here. Go through all of them. It's really good practice. So start hydrogen, helium, lithium, beryllium, all the way down. After neon, we've got sodium, magnesium, and then we skip, so this one doesn't go in order. So if you're doing a pattern, notice after there it stops. And speaking of patterns, after you're done with that, jot down 3 patterns that you notice. If you would like to start it with the phrase "I notice," you are welcome to do that, or if you just want to bullet point your patterns, that's fine too. Pause the video, it'll take you a few minutes. Do the electron configuration for all of those elements, and then we'll go over the answers. Okay, here are the answers. You might need to pause the video again here to double check your work. But take a look at every single configuration. It's very important you are getting these correct while we're just starting, because we're going to be doing some different things with configuration as we go. And double check lanthanum down here and zinc as well, because for those, you had something in the D block, and then lanthanum also went into the F block, so check that as well. And the last thing that you did, you wrote down some patterns. So they could be anything that you wrote down. Maybe you noticed that every single one of these starts with a 1 or a 1s, or that every single time the electron configuration gets larger. That's fine. Those are all great patterns. It's whatever helps your brain remember it. Okay, so now you know what electron configuration actually means is where the electrons are for every single element and where they are inside that element, whether or not it's a really small element and it only goes to a 1s and you've got the first energy level in a small sphere, or if it goes all the way up to maybe 4s and is larger. You know that electron configuration is really just mapping out the shape and energy of all of those electrons in an element.